All right, so today what we're looking at in this differential equations section is it's quite titled Using Definite Integral to Solve a Differential Equation. So here's our differential equation we've got dy dx is some function of x, so this is the gradient function, remember? So the type of questions will say find y when x is b, given that you know that y is d when x is a. So essentially what it's doing is say you've got a point, and given the dy dx, which of course is the change in y with x changing, and you can figure out how x changes between a and b. That's not too hard. And so the y value will change a certain amount. Add that to our original y value, and there's your answer. So, as I said, dy dx is our gradient function. So normally what we do is say, okay, to find y, let's integrate that gradient function with respect to x. And of course, if we're doing that, say from a to b, when we do that, we've got big F here as our antiderivative of little f, and we're going from a to b. And of course, that then is big F with the x value b minus big F with the x value a. And so that gives us our change in y, if you like. So y is changed by that much. And so then what we would need to do is we would then need to add this y here that we started with to it. All right, so the upshot of it all is that y, so when we've got the initial condition a and d, so the upshot of it all is that y would be the integral from a to b of the gradient function with respect to x plus d, and d is our original y value. All right, so that's kind of the gist of it. There's a whole bunch of different ways that can be kind of explained, but that's kind of how I think of it, is that we want to know what the new y value is when x is b. We know what the y value was when x is a. What's the change? Well, the change in those is this bit here, and then that change then would be the change in your y value plus wherever you started. All right, so let's have a look at an example. So here we've got solved that using a definite integral, dy dx equals cos x at x equals pi on 4. All right, so that's our new x value. So that's the one that obviously I've already labelled them as b. So that's our new x value. And here's our originally where we started. We started at x equals 0 and y was 0 at the same time. So a is 0 and d is, in this case, also 0. So we're using, of course, y equals the integral from a to b of fx dx plus d. And fx, of course, little f, is our gradient function. So in this particular case, the y value that we're looking for, it goes from 0 and we're looking for it at pi on 4, and fx is cos x dx plus our d, and that's where we started for our y, so we started at 0. All right, so now we've just got to do what we had done before. So anti-differentiate cos, that comes from sine pi on 4, 0 plus 0, which is not necessary, but I'm just going to leave it all in there. So here we then have sine of pi on 4 minus sine of 0 plus the 0. Sine of pi on 4, of course, is root 2 on 2. Sine of 0, 0, sine of 0, 0, plus that 0. And so root 2 on 2 is our solution, our y that we're looking for. All right, so solve using, it means we've got to find the y. And here we are. We've now found the y at a particular spot using this relationship. All right, so that's doing it by hand. Now, sometimes, of course, we may need to use our calculator to do it, depending on how what they say. All right, so here we've got solve f dashed x is equal to 1 on with the square root of 2 pi e to the negative half x squared at x equals 1, given that f of 0 is 0.5. Now, I've actually got this labelled incorrectly because our original spot that we are looking at is our A, so I've got that labelled incorrectly. So that's our A, and the x value we're wanting it at, that's our B. So I have to go back and alter my notes there so that I get that correct, that labelling there. And then, of course, the y value at x equals 0 is the D. And, of course, all of this stuff here is that function that we're talking about, which, of course, is the gradient function. So let's have a look then. So if that's the case, then f of 1, or the y value, and I'm using the function notation, the fx notation here, so f of 1 would then be the integral from 0 to 1 of all of this stuff, square root 2 pi e to the negative half x squared dx plus where we started at 0.5, and it says to 4 decimal places. So we're going to use our calculator for this. So here's the calculator. So I've got it already entered in. So of course you go to your keyboard. It's in the math 2 is all your differential. So this one here, you put it all in. This one on pi root 2, I used a couple of these two templates. The e to the whatever, again I use templates. Now the bit that I'm going to actually point out to you is this 0.5 bit on the end. Oops. So see there, if I go back and I get rid of that dx, see how there's that box there in the template. That's when you click on there, it gives you the d with the box. So we want x, and so see how that cursor's now little. So if I enter anything now, what the calculator thinks is that's what I'm integrating with respect to. So what you need to make sure you do is click to the right and say, see now the cursor's got big. So now that the cursor's got big, I go plus my 0.5. And then I go EXE, and there we are, and so it's 0.8413 to 4 decimal places, which is what we were asked to do, to 4 decimal places. All right, so had I not done that, let's have a look and see what would have happened. If I had have just gone DX and then I've got a plus 0.5 and EXE, wrong argument type, see, so it's, all right, and that's because, as I said, I didn't bring that cursor out to there to glass through then the plus 0.5. All right, so better go back to here, put the answer, and so that is 0.8413. All right, so that's it for using definite integrals to solve and find that y value. If you are not sure about anything or you want some more clarification, make sure you get some. And as always, have fun.